Welcome to our team submission for Xilinx's 2022 Open Hardware Competition. We are 3 master's students from the University of Strasbourg in France and are excited to give a brief overview of our results in this video. To start things off, our project submission is actually the result of another competition we participated in earlier this year. For 6 months, students in master's programs all over France attempted to reduce the energy consumption of a softcore RISC-V CPU running an artificial intelligence application. This program consists of a convolutional neural network CNN, which is able to recognize handwritten digits from the MNIST dataset. The competition enforced several constraints regarding modifications to the CVA6 core. For example, students were not allowed to increase the execution time of the MNIST application, nor excessively increase the FPGA resource utilization. To identify the best possible optimization targets, we first explored power reports generated by the Xilinx toolchain. We instantly spotted a large power consumption originating from the cache system within the design. After analyzing the program's memory activity, we also discovered that a significant number of RISC-V instructions were of type load. We thus decided to concentrate our design efforts on the CPU's caches. Our initial attempts to modify the existing system were mostly unsuccessful. This was in part due to the sparse amount of documentation that exists on CVA6's cache. We thus decided to start from scratch and create our own, hoping to be better prepared for optimizing its energy usage in our application. Our number one goal was to build a simple cache that could be parameterized for the CNN program. We also made design choices adapted to a memory-intensive application, for example, by opting for a write-back write-allocate cache structure. Here we illustrate a simplified finite-state machine diagram for the data cache controller that our team developed. After having integrated our new caches into the CVA6 CPU core, we achieved a final energy reduction of 10%. Finally, we conclude this presentation with a demonstration of our design on a Zibo Z7 board. First, we download the bitstream to the FPGA board connected remotely to our work server. Then we launch OpenOCD and GDB. These open source tools are necessary to program the RISC-V CPU and to execute the CNN application. After everything is connected, we transfer the program to the CPU and then execute it.